All right, so yeah, Carrie just introduced you to the structure of the data centers. So that's the point where I want to continue. And yeah, the question we are now talking about is how is the data that we actually process at the data centers produced? So in general, SLR observation data is provided in the consolidated range data format. There are also some older formats for older data, but that's the format which is used now routinely. In this format, we have provided two kinds of observation data. The first one is the full rate data. It's the actual observations that the stations have measured, but that's the data that we usually don't process at the data centers. We use the second observation type, which is the normal point data, and it is defined on the ILRS webpage as a type of condensed range observations collected over several seconds to minutes. This means we take our full rate data and kind of calculate an average observation in order to reduce the amount of data that we have to process. In order to do this, in order to form normal points from full rate data, we need orbit predictions for the satellites, precise orbit predictions, in order to be able to say if a data point from the full rate data is accurate enough in order to be part of a normal point. So full rate data and the orbit predictions in the CPF format are the input for the generation of normal points, which are then the input for data processing at the analysis centers. A detailed description of the data formats can be found on the ILRS webpage, but I am now going to give a short insight into the CRD format, the format of the observations. Yeah, basically it's an ASCII-based format, so just a normal text file. You have a header section giving you information about the data format, that it is CRD, the station from which the observations are, the target to which was measured, so the number of the satellite, and the session or the path from which the data stems. Below these four header lines, you have four configuration lines, which basically give you information about the laser system, the configuration of the laser, the detector which was used, the timing system, and so on. Below this, the line starting with numbers, which you see here in gray, you have the actual data. So these data records contain, of course, firstly the range in full rate data, or then afterwards in normal points, and some additional information that you might need for data processing, like meteorological data, the pointing angle of the laser telescope, the calibration, and so on. Yeah, you find the CRD observation format description on the ILRS webpage, which is very important. Currently, we still use the version 1 format, but we are in the process to switch over to version 2. So first stations are already delivering data in this new format, so you have to be aware when programming your software to be able to read both of these formats. Now the question is, what is a normal point? I want to give a short introduction on this. As I said, it is formed by averaging the full rate data over a certain time span, but of course we don't just take the full range that we measure and make an average. It's a little bit more sophisticated. There is a recommendation for this time span over which we average. It's the so-called bin size, and it is basically dependent on the satellite mission which has been observed, and it can range from 5 seconds for low Earth orbiters to approximately 5 minutes for very high satellites. On the right-hand side, you see a plot an example for how such a normal point is calculated. So we take a part of the arc or the path which has been observed in full rate and generate a normal point which is basically in the center of our bin over which we average the data. There is a recommendation by the ILRS Networks and Standards Standing Committee saying that normal points for daytime observations have to contain at least 6 full rate data points, and a nighttime normal point a minimum of 3 full rate data points. This is dependent on the accuracy of the observations due to external effects like the light. Okay, so how is a normal point generated? So in general, there are several approaches, but the most important one is the so-called Hurst-Mousseau algorithm. It is performed in 2 stages. So the first stage is to take our full rate data and perform a data screening in order to determine which of these full rate data points are accurate enough to be part of the normal point forming process. In the first step, as you can see on the right, we just perform a standard outlier determination and remove observations which are obviously too far off our predicted orbit. So we compare basically the observations to the predicted orbit. This is why we need a precise orbit prediction, and have a look at how close these observations are to this orbit. After having done this removal of the obvious outliers, we perform an iterative process for the data screening, which means we solve for some orbital parameters. So we try to estimate, let's say, corrections for this predicted orbit, compute the residuals of these of the remaining full rate observations to this improved predicted orbit, and then again perform an outlier detection. For example, this is just an example that I calculated some time ago. We have 7 iterations, apply a 2.5 sigma criterion, and in the end, in the last plot, we have the reduced full rate data set, which is then the input for the actual normal point generation. So you can see there is, in some cases, really a large amount of full rate data which is in the end not used for the normal point generation because it's discarded in this iterative process. Now the second stage is the forming of the normal points. So we have a set of accepted data points and have our predefined bin size for normal point generation according to the satellite missions. Within each of these bins, we now calculate a mean prediction residual, so these residual to the predicted orbit, and then locate the actual observations, the epoch of the actual observation closest to the average epoch of the full rate observations in this bin. And finally, the so-called normal point is calculated by reducing the actual observation at this point by its fit residual and adding the average fit residual from our bin. So we now have a corrected observation containing the information of all the full rate data points within our bin, but at the epoch of an actual observations that has really been performed by the station. As you can see, for example, for LGS1, where we have a bin size of, I think it was 3 minutes, we had for September 2019 a full rate data file containing 140,000 observations from Wetzel, site 8834, and after normal point generation we have some remaining 311 normal points. Here I plotted it for one pass, so you can see like these maybe about 100 full rate data points now got only 4 full rate points got only 4 normal points that we then use for our data analysis. So, yeah, I guess it might be interesting for some people to do some normal point calculation on their own in order to understand how this process works. And there is a software, it's written in Python, which can be downloaded from this link on the ILRS webpage. It has been programmed by Matthew Wilkinson, who is also here today, and can be used for forming normal points from a full rate data input file. I compiled a little script in order to show you an example for this. So the first step is, of course, that we have to download a file containing full rate data from one of the data centers. In my example, I did it from the EuroLAS data center that we operate in Munich. So it's downloaded from the FTP server. Carrie already showed you kind of the structure of this data center. And then afterwards uncompressed, because these files are in a compressed format to save storage. And we need a file containing the precise satellite orbit predictions, a CPF file, which is downloaded basically the same way. Now, how do we start this program, Orbit NP? The program needs some information, of course. Firstly, we call it by giving it the full rate data file. Then we say, okay, this is our prediction file, and we can define the station. In our case, it's 7841, that's Potsdam, and the normal point bin size, which is 120 seconds for Lagius 1. If one is too lazy to think about which orbit prediction file he needs, he can also choose another option. It's this -A option, and then the program will propose you the correct orbit prediction file, and you can just choose from which predicting center you want to obtain it. Okay, so now we call our program. We decided to start it, and you get some information. So the program is checking the input parameters. We defined basically everything which is stated with a plus in the beginning of the line. What we did not define in our call is the normal, so the minimum number of observations for a normal point. The program uses a default of 30. So each normal point which we get will contain at least 30 full rate data points. Yeah, let's go on. The program outputs a list of all passes of the station that have been that are contained in this full rate data file. In the case of Potsdam, it's 31 passes, 32, and as we have downloaded the CPF orbit predictions file for the 14th of September 2019, we now decide we want to analyze pass number 4. Here on the right you see the date, 2019, September 14th, and see what happens. So we enter pass number 4, and then the software is processing. Again, it's basically performing the normal point process that I explained before. If you have predefined the orbit prediction file, it just uses that one. Otherwise, if you have chosen the automatic selection, it will provide you the 3 alternatives. That's 3 of the prediction centers providing these files. And then we decide, okay, we want to choose the one from Japan, the .jax file, and select provider number 1. Then it's going on. The iterative orbit adjustment starts, so the program is calculating the fit residuals, removing the outliers, and after, in our case, 9 iterations, we get a result. There is also some statistical data or some parameters which have been estimated. And finally, we get our list of normal points. So that pass number 4 of Potsdam on 14th of September contains, how much is it? 6 normal points. And now I put that red frame around this column because it gives you the number of full rate data contained in each normal point. And as you see, it's definitely more than 30, the minimum that the program uses as default. Yeah, and keep in mind maybe the 4th normal point with this large number, 2,900 full rate data points, because now we go to the plot, which is coming out in the end. And there you can also see the 4th normal point contains the largest amount of data. So these 2,900 black dots from the full rate file now form this one green normal point. Yeah, furthermore, you get some additional data for analysis. So in the top, in the left, you see the full rate data ranges. On the right, you then see the residuals to the orbit prediction, which are, of course, comparably small. And here in the big plot, you then can compare the full rate and the normal point data. And on the right-hand side, you also have a histogram in order to be able to judge whether the full rate data is distributed equally around the orbit or if there are any systematics in the data. Yeah, that's basically it. So if anybody wants to test this, the software provides a comprehensive README. Basically, my 2 examples that I showed are based on this README. If somebody needs a file also performing the data download in advance, I can also provide maybe my test program. Then you have the full process from data download till running the program. Yeah, but it's basically quite easy as soon as the program is running. Yeah, to conclude, so the normal points are a robust, condensed input for the SLR analysis, reducing the amount of data to process. So this is very important, especially for the kilohertz laser systems. If you have thousands of observations per second, it's not so easy anymore to process these with a standard SLR analysis program. Yeah, basically a normal point is an averaged observation over a certain mission-dependent time span. The problem that we still have is that there is not only one single normal point generation algorithm. Different stations use different approaches, and it's still a subject to of discussion which one is the best approach. Yeah, so all standard products we have so far are based on these normal points. And then Mattis is now continuing with what we do with this data. That's it.
Thank you, Alex. Any questions?
Yeah, I guess there have been some studies on this. And I think there is also not a clear evidence what is the impact of, or if there is a significant impact from forming these normal points. But yeah, I think it's still an open question, kind of. I don't know a final answer on this. Of the orbit prediction file. Oh, the required accuracy. That's a good question. So definitely we need a precise prediction, but I don't know this right now. So as we are doing an orbit fit, so we also solve for some orbital parameters. It is not so crucial because we are kind of improving this orbit prediction from the full rate data, but definitely it should be not the worst orbit. Yeah.
Were you referring to the prediction orbits or the orbits that are used for the development of products?
Yeah. So
for
the
the
predicted
normal
orbits. Yeah.
Normal points. I think there may be some differences among the centers that are generating them. We had an activity that was run by Matt to look at the normal points and compare using a standard package and comparing the results from some of the stations that may be using some different packages. So he can probably best comment on that, but my recollection was it was certainly, we must be talking about, you know, certainly way below a millimeter. Maybe Matt wants to say something about that.
Yeah, definitely. So this is a point that I think should be considered. Because as you see, you have a large amount of data points which you reduce to one. It can be hundreds of data points. And the requirements are still something like a minimum of 3 or 6. So we have much more data than we had in the beginning, maybe when these standards had been defined. Yeah.
There is a quick answer to this question. We do not have only a minimum number of points per normal point. We also have at least suggested a maximum number. That means if we have, for example, 1,000 points for a given normal point pin, then we switch to the next satellite. And that means in a 5-minute interval, we have the chance to track several GNSS satellites, each given a normal point. Because it doesn't make sense if you have more than 1,000 points, the accuracy is not increased anymore.
Okay, thank you.